stream. And I think we're ready to go.
Welcome everyone to episode 21 of the Machine Learning at HZG seminar and the first episode of 2021. I'm David Greenberg from the m-dml group. We have a really interesting paper that gets at some topics we've discussed before from a new angle. I think, like a lot of the best papers for this seminar, the concept is simple to explain, but the details are interesting and there's some clever things that were done. So the paper, Oliver Watt-Meyer et al. Just came out, collaboration between NOAA, University of Washington, and Vulcan, which maybe I'll touch on a little bit at the end if there's time. And like a lot of previous papers we've looked at, they want to improve weather and climate models. We want to do this with machine learning. And there's a couple of ways we've seen this done in the past. One way is you take a high resolution model as training data and you train a machine learning correction for a low resolution. I believe this was our episode 19. Another approach is to target a specific parameterization in the model. We've seen this with radiation. We've seen this with moist convection a few times. What these guys do is something interesting, right? They don't want to just speed things up compared to an expensive parameterization or a high resolution model run. They actually want to do better than the model in matching the real world. So what they do is they take a run of a climate weather model. I'll get on the model in a second. And they train a machine learning method, in this case, random forest, which we've touched on previously as well, to calculate a correction between the simulation and an analysis data set. So an analysis data set combining observations and inductive biases from simulators as well. So we'll talk about how they did this, what their target data was, what their framework is, and what this could mean. We'll review a little bit of the material and talk about where the data come from and explore their results, which I think are interesting. It's one of these ideas which for me is like, it's easy to say, oh, that's very simple, but my first reaction is, well, I wish I'd thought of that. This is actually very clever. Okay, so yes, this is a basic idea here, right? We have the state of the model, which is an atmospheric model. The ocean surface temperature is prescribed. All the model variables A have tendencies in time, or time derivatives, which are composed of an advection part, an in-place physics part. This is a standard distinction between dynamics and physics we see in a lot of these climate and weather models, and this additional term, which is really the substance of their technique, right? So we have, if you just run the model on its own, from any initial conditions, it'll evolve over time. You can run it for a day, you can run it for several years, as they do indeed both of these things. But what they do at each time point, instead of just running the simulator, they calculate the difference between the state of the atmosphere in their simulation and the state of the atmosphere in a reanalysis from real world data. And they add an additional term to the derivatives in time of all the atmospheric variables, wind speed, pressure, temperature, moisture, so that they approach the reanalysis data over time. And they do this with a tau, a time constant of about 6 hours, so that while the model follows sort of its own rules on short time scales, its own rules for advection and physics and so on, it drifts back to match the observational analysis over time. So this is no machine learning yet. This is just a way of running a model with an extra term. And they do this. So which model are we talking about? I found it very interesting to read about this model. I didn't know about it. And it kind of readjusted my sense of what's out there. I'm sure this is very old hat to some of you. So this is a finite volume method of the global forecasting system of the United States. Being from the United States and well aware of its problems with the decaying infrastructure, I found the story of how this model came about sort of interesting. In the early 2000s, the old GFS system, which worked like many models with a harmonic coefficient-based dynamical core, and at a relatively coarse resolution, failed pretty dramatically to predict that Hurricane Sandy was going to flood New York. And then, everyone, I remember a lot of my friends were, using candles for a couple of weeks after that. Meanwhile, the European model from ECMWF had absolutely no problem predicting in several days in advance of what the GFS did. So it turned out that the infrastructure was underfunded. They didn't have enough compute time. Also, the old model needed to be updated in several ways. So it's a finite volume model. Instead of only using spherical harmonic coefficients, although interesting, I guess IFS and the ECMWF also uses spherical coefficients. But it uses a cube sphere, like some of the convolutions we covered in episode 2, right? So it divides the sphere into 6 overlapping faces, which it maps onto a cube. It supports nesting just like ICON. So in many ways, I was very interested to see how much this does resemble ICON, both in its goals, supporting huge parallel computers of the future, and its features, the nested grids, and the fact that it's a finite volume method. There's important differences. This is a cube sphere, ICON's a icosahedron. This is a rectangular D-grid, FE3GFS. So ICON is a triangular C-grid, but there's a lot of interesting commonalities here. You can see on the right is beautiful simulation, and indeed, unsurprisingly, a lot of the papers on the new model show how good it is at predicting hurricanes. I guess it's now a real contender. Another really interesting thing when looking at how they generated the data for this model, right? So if we go back a couple slides, we have to do simulations and we have to nudge them. And then we'll eventually use this to train machine learning methods, and then we'll put the machine learning methods back into the coupled model. Well, what they have is very nice. If you look at this paper, McGibbon is actually from this Vulkan company. They have Python wrappers to get the model state at different points. So some of you, I know some of you, and I've worked with some of you on trying to get the model state out of some of these climate models. It's not an easy thing to do. And the fact that they have these Python wrappers to view and modify the model state at different times is a really great thing that I think all climate models should do. Okay, so the method that they use to calculate the tendencies. So the strategy is, this is just a nudge simulation, right? What we're going to do is train a machine learning method to predict the tendency that would be required to nudge the model state toward the observational analysis. And we're going to try to guess this tendency simply from the model state itself. And the method that we're going to use to do this is a decision tree for regression, in particular a random forest. So the idea here is that you have your input space, and you divide it into spatial regions. You learn one output for each spatial region. You have these trees. You have a selection of these trees where you look at random cuts of the input space in different orders. We covered a lot of this stuff in episode 19. Just to give a brief review, I'm showing this figure, but this is the basic idea. So they have advantages and disadvantages. I'll touch on some disadvantages in my view here at the end. The authors do as well in their discussion. But one nice advantage that you can see, so the data here are the red dots, the decision trees are blue and green, is that even if you go outside of your input data range, even if you go to new data that you never saw during training, you're never going to predict outputs outside of the range of previous outputs. So it's not going to go to infinity on some expected data. And this is good for numerical stability, as we saw in episode 19 when we covered Yuval et al. Okay, so this is a tool they use. It's a bit simple. So what are the inputs and outputs? The inputs are location specific. So at a specific location in the grid, this cube sphere grid, in a particular place in time, we have temperature, specific humidity, eastward wind, and northward wind. These are what we're trying to predict. The inputs, temperature, specific humidity, eastward, northward wind, land, sea ice mass, and surface geopotential, and the cosine of the solar zenith angle, which basically gives you the time of day. So if we were dealing with some neural network that could take the whole model state as an input, it could look at neighboring locations, it could look at image features. What we're doing is just looking at the atmospheric variables at one point in space and time and use this to calculate derivatives at one point in space and time. The disadvantage is we are discarding a lot of information, right? Like if we look at a surrounding neighborhood, we might get a much better guess of the tendencies. But the advantage is by dealing with low dimensional inputs and outputs, we can get very nice fits with these decision trees. And we don't have to have a perfect result. We just want to do better than the original model. So they fit 16 different trees. These make up a forest. Again, episode 19 has details. And they can cut up a space up to 13 times. Okay, so this is our architecture. It's pretty simple. Let's see what it can do. First, how do they measure the results? For the variables which they nudged in the simulations, that is, the variables in the atmosphere which were adjusted using this nudging term, that's moisture, temperature, and winds and surface pressure. They just use the nudge simulation as a ground truth. This is maybe a debatable thing to do, but this is what they do. For precipitation, which you wouldn't expect to be captured by the nudge simulation too perfectly because it's very difficult to capture that, and there's a lot of stochasticity. They use an observational data set. I'm showing you one image. I believe this is June 2011. This is the kind of data that they're comparing to when they try to measure the accuracy per day, per year, overall biases in their precipitation. And there's something interesting that's happening with the precipitation, right? Because they're nudging moisture, that moisture has to go somewhere. So when they nudge the moisture in the atmosphere down, that makes precipitation. When they increase the moisture, that is reducing precipitation down to a minimum of 0. So their nudging actually affects the precipitation, which is diagnosed from their model. Okay, this is a basic framework. This is a good time to take questions if anyone doesn't understand anything. I'll just take a quick look at the chat, empty so far. Yeah, but just to recap, we have a nudge simulation, and our goal is to use the decision tree, the random forest of decision trees, to guess the tendency which would be required to nudge our model toward observations based only on the local state of the atmosphere. This is what they're trying to do. Very simple idea. I wish I'd thought of it. So this is how, so let me explain what we're seeing in figure 2. So first, the target. This is the heating. So if we look at A, this is the nudging that was applied in the nudged simulation. This has nothing to do with the random forest yet. There's no machine learning. This is saying if we nudge our simulation to observational data set over, I believe it was 2015, the entire year. If we do this nudging, how much are we on average heating or cooling the model as a function of spatial location? And you can see we're cooling some places, we're heating others. Overall, we're heating, which means the model had a cold bias. And then on the right in B, we can see if we give the random forest as input in every spatial location, in every vertical level, and every time point, the local atmospheric variables, it will calculate an estimated nudging factor, which is supposed to make the model behave as if it were being nudged toward observational analysis. And it does a pretty good job. Overall, it's heating as it should be. Overall, it's heating sort of in the right places. You can see where the nudge simulation gets hotter, so does the machine learning nudge simulation. It doesn't capture all the fine local features, but it does a pretty decent job. On the bottom, we have the same story, but with moisture. You can see and this took me a little while to unpack. I'll try to go slow. It's a little counterintuitive in places, but the nudging in C that would have to be applied to the model to get it to look more like observational analysis, this has a negative moistening. It is making the atmosphere more dry. In so doing, because that moisture has to go somewhere, it's actually increasing precipitation. So the FE3 GFS did not rain enough overall, and in some places it rained too little. You can see it's actually moistening the atmosphere, which reduces precipitation. But this is the overall effect. You can see some interesting stuff as around mountain ranges, the Rockies, the Himalayas, the Andes. And you can see, at least to a reasonable kind of slightly blurred out approximation, the random forest is calculating more or less correct moistening, right? And generally negative moistening, that is an increase of precipitation and a drying out of the atmosphere, as it should be. So the idea is that not in any coupled model run, but just taking the model atmosphere state, the random forest tells you, should I be moistening or drying the air to make this look more like observational data? And it does a pretty decent job. We have the same story for wind. You can see it's not quite as perfect here. There's some issues. I think part of the problem also is that we're nudging with a 6-hour time delay, and wind is going to do a lot in those 6 hours. So we may be, going for a moving target. In any case, overall, it nudges the model as if it were being nudged to a observational analysis. If we look at the overall increase in, if we look at the correlation of the nudging tendency from the simulation nudge toward the observational analysis, and we compare that with the nudging tendency output by the random forest, we can look at that as a function of how far we are from the equator and how far up we are in the atmosphere. You can see in some places, especially in the mid latitudes and the lower atmosphere, we have very high correlations. In other places, it's closer to zero. They say overall, they're getting about 30% of the variance. Okay, so overall, it's doing what it's supposed to, but the question is, when we actually plug this machine learning tool, this random forest, back into the model, and we couple it back to the model, what's going to happen? And actually, it's not so bad. So these are medium-term forecasts. What they're starting with is a atmospheric state. They don't quite spell this out in the paper. Someone jump in if you manage to figure this out. But I believe this is initialized with an analysis state. And then they look at the analysis in the future, and then they look at the nudged model run where the nudging is now provided by the random forest. So the observational analysis is not available for nudging, but because we used it to train the random forest to output the correct nudging tendency based on the local atmospheric state over the 2015 data, here, testing on 2016 data, we can see an improvement in the match. So lower is better. This is the error between the future state of the analysis, or maybe of the nudge simulation, compared to the original simulation without any nudging in black versus the ML corrected random forest nudge simulation in red. And the differences may not look too big, but when you look on the x-axis, we're talking about a good half a day or more. This is a real improvement in our forecasting ability. And we see nice improvements for the geopotential height. We see it for surface pressure, and we see it for the temperature of the lowest layer. They went a little further in the bottom row is taken from the supplementary material. They asked, okay, well, what is actually causing this improvement in predictability? Why are these nudge models actually matching the future analysis states better? Is it, for example, if we talk about temperature or pressure, it could be because we're directly nudging temperature and pressure correctly, or it could be because we're nudging wind better, and this has a secondary effect. So to investigate this, they also trained a second version of the random forest, which only nudges moisture and temperature. That's in blue, and you can see it doesn't make so much of a difference for the performance of temperature and pressure. It actually does a little bit better for the 500 millibar geopotential. For surface pressure, it actually doesn't get the right answer at all, any better than the original baseline model. So this really, you really need to nudge the wind speed to do this. Okay, so they did a little bit of investigation of what worked. It's always nice to see open the black box a little bit. And then another test is to see how well this is always a good thing to do. How well did this approach predict something which wasn't built into the training? So it wasn't trained on precipitation, it was trained on moisture. But it's much more difficult to predict precipitation than it is to match the moisture of a reanalysis data set. And so they looked at, on left we have the baseline. If we look at the overall 2016 average of the unnudged, uncorrected model compared to a GPCP observation product, we can see it rains too much in some places like Alaska. It rains too little in some places like in the Amazon basin in Southeast Asia. And what we can see is that after using the random forest, we have a reduction of maybe 25% of the error and the bias in precipitation. So this is a significant improvement at a computational cost of about 10% extra for the whole model as described in the paper. So not too bad. You can look in a little more detail and see not everything is quite so perfect. You know, the precipitation is improved, surface pressure is improved. Other things are not so great, like the temperature in the upper atmosphere at the poles can be off by 30 degrees. So this is not great. It was already sort of not perfect in the original simulations, but this actually makes a few things much worse. This is something always to keep in mind. So this is basically the story. They got some nice improvements through a simple idea. Instead of nudging to a high resolution simulation or an expensive super parameterization, they just nudge directly to the real world, which is a very nice idea. And it's, I think, in closing on this paper, I just want to say, I find a little interesting this. I looked up what is this Vulcan Incorporated. It's a research foundation owned by Paul Allen. I've kind of complained a little bit about corporate science of some of the tech giants in a few other episodes and said, well, you know, they do all this nice work, but then they use just a ton of computational power and they don't share their code and you can't check it and you can't use it. And it's just kind of building up the intellectual property of these huge tech companies. This is quite different. They provide their own, they provide their code on GitHub. They, including these Python wrappers for, you know, interacting with the model. It's, this foundation was created by Paul Allen of Microsoft. He also created the Allen Institute of Neuroscience, and it fits in with a number of these kind of charitable foundation research institutes. The Simon Center is another example in biology and mathematics. So that in addition to kind of the corporate science, there's also apparently a lot of, say, independent foundations with corporate money, which are actually doing some interesting work, and they'll fit into the research landscape in an interesting way. Okay. So that is the basic gist of the paper. We maybe take a few questions now, and then I think Marcel, you wanted to describe some related work that maybe relates back to episode 18, and there are some connections to this paper by another paper from that group.
Yeah, just 1 or 2 minutes probably.
Great. So any questions, any comments, any thoughts on this approach?
Hi. So they used random forest to do this here, right? And they show that it provided some skill and was quite successful. But they even said it was limited in some way. Do you think we could use more advanced machine learning techniques like neural networks and use the same data sets to just train them on them and maybe receive even better results?
Yeah, I think that's a great question. In fact, they mentioned this a little in the discussion. So they talk about the idea of using ML. Neural networks also show better skill than random forest and offline tests. This is not necessarily a key factor for online skill. I mean, right. There's a lot more information they could have provided. One thing is they don't, as far as I could tell, they didn't even tell the random forest what the latitude and longitude were or what the vertical level was for the atmospheric variables that were being provided as input. So this could be useful information. It's also quite likely that each grid point and each vertical level has information that would help compute accurate tendencies for neighboring grid points. And there may be even global features of the atmospheric state which could be used to improve all these local tendencies. But once you start growing the inputs more and more and more, it gets very difficult to use random forests. They mentioned that they already started having memory problems. So the random forests they didn't use many, I think 13 trees in their forest and a depth of 13. That's not so much compared to what we saw before, but they were already beginning to deal with, I think, 360 megabytes to store this, which was significant compared to the rest of the memory cost per processor for this climate and weather model. So, so 360 megabytes of memory was a lot, but 10% wall clock time was not. And this is a pretty coarse resolution model. So, yeah, I think if you wanted to provide all this extra information, neural networks would absolutely be the way to go. And in particular, maybe some of these spherical convolution networks that we covered in episode 2. There's a question from the chat. I can find the chat. I struggle. I really struggle with Zoom. Felix Stiller from DKZ asks, couldn't the problem of correcting errors basically be as hard as making the predictions themselves, at least if you want to get it close to zero? If so, this seems to potentially only lead to temporary successes. I'm not 100% sure I understand the question. Felix, if you want to chime in and elaborate a little bit, maybe it's something to do with short-term versus long-term predictions.
Hello, can you hear me?
Hear you fine.
So the thought was, I mean, if I was a little bit late to the seminar, I'm sorry, but if I understand it correctly, this random forest basically tries to correct the predictions of a classical model.
Yeah. And well, correct the tendencies, the time derivatives, all the atmospheric variables. Exactly this nudging between the free running model and the observational analysis. It wants to calculate these corrective terms, these additive corrective terms to the time derivatives, so that they behave more like the observational analysis.
Yeah, and the thought was that maybe if you want to get the error to zero, or basically perfectly correct them, then isn't that just as hard as making the predictions themselves? I mean, do you need to fully understand the problem to fully correct also the errors? And thus, why not make the predictions themselves, right? I mean, basically this seems to be only like lead to some local optima in where the random forest can kind of guess where the network is wrong, and it can correct some of those frequent errors, but it's gonna get it wrong in other cases, as has been shown. So this seems to, I don't know. I mean, if that would work perfectly, you could just like ditch the classical models in general, right? So
Right. I mean, there's a couple of factors at play here, right? One is the fact that by learning a correction, you're still harnessing all the scientific knowledge and hard programming work that went into making that climate and weather model that the US government finally found money to fund after New York went underwater. The trouble is, if you throw that away, you have to learn everything. This is a much, much more difficult problem. You have to deal with a lot of things that aren't even covered in these 4 variables, like coupling to ocean temperature, like radiation. You'd have to learn everything. And by kind of being modest and just trying to do one thing well, they did a pretty good job. We saw this with Yuval et al. In episode 19 as well, by specifically targeting only moist convective processes. They really did a good job there. And it may be that the differences between the original model and reality are smaller and easier to learn than learning a dynamical representation of the full real system from scratch. That the corrections are less difficult than learning the whole model. This is one possibility. The other thing is just from a structural point of view, these random forests only take local inputs and give local outputs, right? There's no information exchange between Z levels or between neighboring grid columns of the cube sphere, as far as I can tell. And that means there's really no way of handling processes like convection, like advection in this framework. You'd have to use something much more powerful.
Okay.
So I hope this addresses the question. I mean, there's certainly a line of work which does throw away this model. We covered MetNet in one of our early episodes, and this is where we throw out the model. We don't try to learn a correction for it, and we just learn a purely data-driven precipitation nowcasting scenario, and it gave pretty decent predictions. What we managed to do here is actually improve the overall biases of the model, which I think could be used then. The idea is, having done this for 2015 and 2016, the hope is maybe it could perhaps be used in other scenarios where you do longer climate modeling runs. Although they mentioned some limitations of that in the discussion as well. It's an okay answer to a good question. Anyone else have something they want to mention? I had 1 or 2 notes on this paper. So, yeah, this is partly addressed by the paper, but when reading this, I was wondering, why nudge to the current observation values? Wouldn't it make a little more sense to nudge to the future state so that weather actually happens at the right time? They're definitely going to get some weird effects in the day-night cycle, which is the model is going to have to deal with. I don't know. I also found it interesting that surface pressure is nudged in the hindcast, but the random forest doesn't do anything with surface pressure. It only deals with wind. And then one more observation I had. I don't know, maybe someone who does data assimilation or weather forecasting can comment on this. Is so trying to understand what exactly the errors at 0 mean here in these forecasts. They're not 0 at time 0, but they don't seem to approach 0 as the forecast delay goes to 0. So how are they initialized in such a way? Is there some 40var or ENKF being used, or are they just initializing with a nudge state? I don't quite get where that jump comes from. So Hai is asking a very good question. is observation data available on the surface only or only on vertical levels? So this is a little bit of a tricky point. Let me go back to, am I sharing? I've been sharing my PDF the whole time or what? Let me share my whole screen. Okay, so if we look at the, so when they do the nudging, they're nudging to the observational analysis, which is on all the vertical levels. When they evaluate the performance, they use the nudge simulation as ground truth, which is kind of a somewhat questionable thing, again, because of the 6-hour time delay. For everything except precipitation. Whereas the precipitation, they used this, what is it called? This data set we talked about. This, I'm not finding it, but this this daily precipitation thing that I showed, the 2011 June example, GPCP version 1.3. So they train it on reanalysis on every level. They evaluate precipitation on the surface. Okay. Any other questions? Any other thoughts on this? I really like this paper. Okay, if no one has anything, or if everyone's still thinking, Marcel, do you want to do this comparison to this other paper you were mentioning?
Sure. I will just quickly grab the screen then.
David, actually, I was too slow to unmute my microphone. I would have a question regarding when in time the correction happens, whether that could cause some instabilities. As you said, some things should be corrected for the future values and some things are corrected in the past. Whether if you see this as a time-stepping algorithm, you should worry about instabilities introduced by this type of correction, or whether one should have a careful look on which variables to correct when.
Yeah, they do. That's a very good point. So they mentioned this a little bit in their discussion. So ideally, you would have a training data set where it's nudged in such a way that it really follows the observations closely. The problem, as they mention, is that below 6 hours, you start to have strange interactions between the nudging timescale and the timescale of winds and turbulent processes. And they said they tried a version where I believe they nudged moisture and temperature on a 24-hour time constant and wind on 6 hours, or the other way around. And they found this just performed worse. So they did explore this a little bit, but I agree that this overall nudging with a time constant approach isn't totally satisfactory and is bound to introduce some kind of strange errors. What would be nicer is if we had a way of training this such that it behaves like observational analysis without having to nudge it. But I mean, this basically means differentiating through the simulator, which is generally not possible in these models.
Yeah, probably they are too complex to do some sort of differentiable programming and actually have a look at this.
Yeah, I mean, there's some new models where they're trying to re-implement the whole thing in an auto differentiation environment. And maybe we'll cover one of these at some point. This Oceananigans model is pretty interesting, but in general, most of these models don't support that. All right, so Marcel, you want to describe the connections of this paper to Farchi?
Yeah, I just wanted to point out that this kind of work where you learn a correction factor to an existing model is, it's not the only type of this, not the only recent publication that goes in this direction. So in, I think, episode 18 it was, we actually looked at a line of work from Marc Bouquet et al., where they did try to learn dynamics models from scratch from data. But one thing that the same group has recently picked up in a couple of their publications is also that they have this this kind of structure where they have a baseline model in their notation FO of X, and then they try to learn a machine learning correction to that. So if you compare these two equations, they're very similar. So this is something they discussed in this paper that I very quickly want to just showcase as a possible place to look for alternative approaches to what we've seen today. They don't do this, they do something slightly different. They don't have an additive correction term on the tendencies. What they have is directly on the prediction of the next state. So they have a model which predicts from a current state X, the next state, which is a baseline model, which includes not only the tendencies, but also the temporal integration. And then they learn a machine learning model that is additive. And these kind of machine learning models, then, unlike in the study we've seen right now, these aren't trees or forests. These are the neural networks again, as was already asked, what would happen if you use them? And then they're training this with mean squared error loss, which was also mentioned in the paper we just had a look at. So this is what this would also look like for the forests. They would have the same kind of scaled squared loss. And the target in this case is also xk+1, which would be the observation in the future. As David was already mentioning, it's not always clear if you want to actually nudge and get the correction factor to the current one, or if you actually want to correct towards the future observation. In this case, where they do it not on the level of the tendencies, but on the direct time stepper, there's not much choice. And then they learn this machine learning model also to do this difference between the observed state and the predicted state under the baseline model. And when they do this correctly, they're going to get this corrective additive factor, which works very, very similar to what we've seen today. They do it on the quasi-geostrophic model, which is a bit simpler, much simpler than the model we've seen today, and where you don't have to deal with questions of Python wrappers for Fortran code and these kind of things. But for this kind of very simple model, they also show that including the neural network corrective term can also decrease the error by quite a bit if you look at the color bars here. So just as a quick pointer that also from the more technical side, people are working on learning corrective factors for existing models. And they have a bit more of the neural network machine learning approach to this already that we've been asking about before.
Well, Marcel, can I ask one or two questions here?
Sure.
So first of all, when you say forecast error, are they forecasting in some kind of data assimilation scheme? How are they doing that?
Yeah, so as the title of their paper suggests, they are doing everything inside a data assimilation scheme. So they don't necessarily assume that they have perfect access to some ground truth data. They don't assume that they necessarily always have the full states, these kinds of things. In this case, how their data is coming about is that they have a sequence which comes from a ground truth model, in this case, a quasi-geostrophic one, and then their baseline model is a perturbed quasi-geostrophic. So everything here is on synthetic data, and they get their training data xk+1 and the model prediction just from running the baseline model on the observed state at every time point. So there's no nudging here.
But the 40-var scheme is a 40-var data assimilation scheme or ENKF or something else?
They want to use the corrected model for 40-var.
So they
In order to-
differentiate through everything. And I guess also during training, in that objective, you can see they're minimizing an error k time steps in the future as a function of their neural network, which means they have to differentiate through the simulator. No, they don't, do they? They don't.
Careful with the indices. It's always k+1. So k is the time index here, not the offset.
Oh, I see. So they don't need to differentiate through their simulator.
No, they actually also discussed this issue in the paper, in the manuscript. If you want to do certain things, you will need, and especially multi-step things, you will end up having to differentiate through the baseline model, which you also acknowledge is something that in most cases is not very feasible.
But they can do it in their QG because they have some special QG that provides gradients, huh?
I'm not sure if they actually differentiate through the baseline model in this. Again, this is always t+1, where k is the time index here.
Okay. Okay, thanks.
Yeah, this would just be it. So just as a pointer that there's also other papers looking in this direction.
It's quite interesting. Okay, any other questions, comments, announcements? I have an announcement, which is that in 2 weeks, we will have Axel Seifert on to present a really interesting paper on microphysical parameterizations and machine learning. And I will send out an email announcing that very soon. And I guess that's it for us for today. Thank you very much to everyone who joined. Happy New Year to those of you I haven't spoken with in 2021 so far. And we will see you again in 2 weeks. Suggestions welcome. Bye, guys.
Bye.